Sumaya Anwar and I'm a Research Fellow and Statistician at CRD. In this session, we'll be looking at how to estimate treatment effects. So, first of all, what exactly is an effect estimate? An effect estimate could be a number that summarises the value of an intervention, such as how many people died or were cured, or by how much their condition worsened or improved. Alternatively, it could be a comparison between interventions, such as how much your chances of survival improve when you start a new treatment, or by how much people improve when they're on this new treatment. When calculating effect estimates, there are three possible outcome types: dichotomous or binary, continuous, or time to event. In this presentation, we'll mainly focus on dichotomous and continuous outcomes. The first type of outcomes we'll look at are dichotomous. In these outcomes, each participant can have one of two possible values. So a patient could either be alive or dead, healed or not healed, pregnant or not pregnant. There are no other options. We'll start by comparing two groups with dichotomous data. On this slide, you can see a 2x2 contingency table that compares people who drank standard coffee to people who drank decaffeinated coffee. You can see that for the 24 people who drank standard coffee, 6 people developed a headache. And of the 36 people who drank decaf, 8 people developed a headache. So our research question is caffeine causing headaches? The first effect estimate we'll look at is the risk of having a headache for people who drink standard coffee. Mathematically, the risk is the number of people who experience an event divided by the total number of people. Using the numbers given in the table for people who drink standard coffee, the risk of a headache is 6 divided by 24, which is 0.25 or 25%. In words, we can say that the risk of having a headache was 1 in 4 or 25%. The next effect estimate is the odds of having a headache. The odds is defined as the number of people who have an event divided by the number of people who don't have an event. Using the data in the table for people who drink standard coffee, who experience headaches and those who don't, the odds of developing a headache was 6 divided by 18, which is a third, which we can approximate to be 33%. In words, we can say that the odds of having a headache were 3 to 1 against, or that one person had a headache for every 3 people who didn't. We can compare the risks of two groups by calculating the relative risk or the risk ratio. The relative risk is the risk in the experimental group divided by the risk in the control group. For our example, decaf is the experimental group and standard coffee is the control group. Therefore, the relative risk is 8 over 36, which is the risk in the experimental group, divided by 6 over 24, which is the risk in the control group. This simplifies to be 8 over 9, or we can approximate it to be 89%. In words, we can say that the risk of a headache when drinking decaf is 89% of the risk of drinking standard coffee. We can also compare the risks of the two groups by calculating the risk difference. The risk difference is the risk in the experimental group minus the risk in the control group. If we calculate the risk difference is 8 over 36, which is the risk in the experimental group, minus 6 over 24, which is the risk in the control group. This simplifies to minus 1 over 36, which is minus 0.028, or a reduction of 2.8%. Therefore, we can say that drinking decaf reduces your chance of a headache by 2.8%. We can also calculate the number needed to treat, which is the number of patients that need to be treated for one patient on average to benefit from a treatment. The number needed to treat is 1 divided by the risk difference. In the previous slide, we calculated risk difference to be 0.028. So if we calculate the number needed to treat, it's 1 over 0.028, which is 35.7 approximately, which we can then round up to 36 people. So we can say that in order to prevent one headache, 36 people must switch to decaf. Similar to a relative risk, we can also compare the odds of two groups by calculating the odds ratio. The odds ratio is the odds in the experimental group divided by the odds in the control group. The odds, if we calculate the odds ratio, it would be 8 divided by 28, which are the odds in the experimental group, divided by 6 over 18, which are the odds in the control group. This simplifies to 6 over 7, which is approximately 86%. And so the odds of a headache when drinking decaf is 86% lower than when you drink standard coffee. The next type of outcomes are continuous outcomes. These can be measurements that can take any value, such as height, weight, blood pressure. But measurements that take numerical values are often also treated as continuous. These can be measurements on pain scales, depression scores, or quality of life scores. In this example, we'll compare the mean average irritability score for each coffee group. Of the 24 people who drank caffeinated coffee, the mean irritability score was 20, whereas for the 36 people who drank decaffeinated coffee, the mean irritability score was 32. The mean difference is defined as the experimental mean score minus the control mean score, which is 32 minus 20, which is equal to 12. We can also calculate the percentage mean difference, which is the mean difference divided by the control mean score, which can be calculated to be 12 over 20, which is 0.6. We can say that decaf coffee increases irritability by 12 points, or 60%. However, an important thing to keep in mind is that not all studies use the same measurement scales, and mean differences depend on the scales used. So in order to make values comparable, the scale must be standardized. One common method is to use the standard deviation of measurements to calculate the standardized mean difference. The standard deviation is a measure of the variability in the data. Over here we have two studies, Smith and Jones, which report the mean irritability score for the caffeine and decaf coffee groups, as well as the standard deviation for each measurement, which are given in brackets. The standardized mean difference is calculated as the experimental mean minus the control mean divided by the overall standard deviation. For the Smith study, the mean difference is calculated to be 32 minus 20, which is equal to 12. As both experimental and control groups have the same standard deviation, which is 6, the overall standard deviation would also be 6. Therefore, the standardized mean difference would be 12 divided by 6, which is equal to 2. We can do the same calculation for the Jones study, where the mean difference would be 8 minus 5, which is equal to 3, and as the standard deviation is 2, the standardized mean difference would be 1.5, which is 3 divided by 2. The final outcome type is time to event or survival. Time to event outcomes are different from dichotomous and continuous outcomes in that they consist of two separate components. 1, did an event occur? And 2, when did this event occur? If an event did not occur, the time until last follow-up is recorded, which is known as censoring. Censoring indicates that the follow-up period ended before the event occurred. There are two ways the effect estimates of time to event outcomes can be calculated. The first way is to calculate hazard ratios, which take the time to event and censoring into account. If you don't have sufficient data to calculate hazard ratios, you could transform time to event data to dichotomous data and then calculate effects accordingly. However, this analysis is simplistic and does lead to a loss of information. While we have calculated effect estimates in this presentation, it is important to note that effect estimates should never be presented on their own. They should always be accompanied by their uncertainty. This uncertainty can be expressed as standard errors or as 95% confidence intervals. These uncertainties require more involved calculations, and so they won't be covered here. An easy option is to get your computer to calculate them for you. Briefly, the standard error measures how far the mean of the data is likely to be from the true population mean. Similarly, the 95% confidence interval is a range of values in which we think that the true population mean lies. The wider your confidence interval, the more uncertainty there is in the estimate.